Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the AAS Journal Author Series. And I am super happy to have Jane Greaves with us today. Hello, Jane.
Hi, great to be here.
Well, it's so nice of you to be here to talk about your very lovely research note. And Jane, where are you located there?
I'm in London in the UK at the moment. Yep.
All right. So is fall happening in the UK?
It is. We're starting to have some colourful trees. We had a really warm early fall, and now it's getting beautiful.
Very nice. And it is October 23rd, 2023, as we record this. And we have finally turned the corner in Phoenix, so we are heading into our fall. I wouldn't say it's cool yet, but we're heading into our fall, so it's very cool. That's an awesome Chinese jacket you got over your left shoulder.
Yeah, that's right. Yeah, I like colourful things, and I like making my own stuff, you know.
Oh, you made that?
Sweater.
You made that?
Yeah. Not the jacket, the sweater I'm wearing, I did, yeah.
Cool.
But I like the history as well, so that's a antique jacket.
Beautiful, beautiful. And Jane, what do you like to do for research?
So I've always been fascinated since I started reading sci-fi in my teens about the idea there's other life out there in the universe. So I try and research whether that's really a possibility. So I've done a bit of work in the solar system, so some studies of Venus clouds that are really exciting and happening with a wider team. And then I like thinking about habitable exoplanets as well. So as we discover these smaller rocky worlds around other stars, like how much could we push that to say, could they really be habitable?
Cool. Very nice. And that is going to bring us to this very awesome research note. It is open access. It's the open access era, people. You can go grab a copy, go get one. When were the first exocontinents? And Jane, take us away.
Well, the first criticism I got was somebody on Twitter, well, not directly aimed at me, saying any paper where the question starts the title starts with a question mark is bound to be wrong. And I was like, can I not even ask this? So I thought that was good. When were the first exocontinents? So cool. If we have some rocky planets around other stars, maybe sun-like stars, kind of my focus here.
Yeah.
Did they have surfaces in the sense that we think of the Earth today? So oceans and continents, yes. Particularly rather than just ocean or just like a desert surface.
Okay, cool.
So I got interested in whether we could possibly calculate this. And I was intrigued by reading papers a little while ago saying we can actually detect radioactive isotopes in the atmospheres of stars. Which I think is incredible because thorium is generally the one we can do. A very small number of stars, uranium as well. But I'm amazed that these are the two least abundant elements in the cosmos that you can possibly study in the atmospheres of stars. So I got intrigued by knowing that these are elements that kind of power the motions of the Earth's crust. Whether we could use these abundances in stars and say anything about the planets that go around them.
Cool. I'm with you.
Okay. So this was actually my mini lockdown project because it seems a long time ago now, but when we were all heavily locked down, I didn't have proper computer access, but did have online journal access. So I was like, maybe if I slowly compile an enormous database of stuff we know about stars, I could come up with a hypothesis that might be testable about any planets they might have. So cool. The planets here are hypothetical. We don't know of most of these planets yet, but there's a lot of atmospheres of stars studied and abundances measured. So the idea was to use, as it says here, things that we know represent like what a planet is. So an iron core and a mantle that's like silica, magnesium, aluminium, and oxygen, stuff like that. And then the kind of power source for that, which is the major one at the present time, is these radioactive elements.
Okay. Good. Yes.
So I simplified this a lot, partly to get it in as a research note and partly to honestly admit this is not my field. I'm capable of writing an equation, but I really want people who know what they're talking about to go, and do it properly. So there is a huge amount of simplification here. As we just saw, actually, the paragraph a little higher up, what the heating does to the mantle of a planet is a lot more complicated than I've represented it. So lots of things would change, like the viscosity and the turnover inside the mantle and things that I can't calculate here. I was trying to simplify it to one number that we could do. Okay, so I kind of have two numbers. I have how much mantle of the planet you're trying to heat, and how much heat have you got.
Okay.
So two terms.
Okay.
So the first one is how much radioactive heat have you got by measuring thorium in the star's atmosphere and saying that goes into the planet. And the other one is if there is potassium. So the thorium is a radioactive isotope, but the potassium, we actually can't measure this, rather rare, radioactively decaying, but we can measure normal potassium. Okay, so if those two are there, then you've got some budget for the amount of radiogenic energy. And we know the half-lives of these elements, so we know how long that lasts. So we can go from what is measured today to what was the heating in the past and what was the heating in the future, or what will it be. Okay. And then the slightly easier bit is how much core to how much mantle does your planet have. So you could do that more complicatedly, but I'm like, here's the basically iron core, and I'll use silicon as a proxy for the amount of mantle. So your planet might have more or less core to mantle compared to the Earth. And that's kind of all you need. So finding stars that had all of these things turned out to be a lot of cross-matching catalogs. And then finding, as it says there, ended up with not even quite 30 stars. It's actually the potassium that's very badly understood for dwarf stars, I think.
Yes. Yes.
So that was kind of a limit.
Yes.
And then I wanted to make sure that we knew something about these stars, how old they really were, when the planets might have been born. So I went to the enormous Gaia database, which now has really nice multiple estimates of ages of stars, and took only the ones where we could do that. Okay, so that was all the inputs.
And at the end,
and then we have the equation.
29 stars. There we go. And then we're going to do a little radioactive decay. And here we go with thorium and potassium.
Okay. So it's all done relative to the Earth now. So the abundances, the things in the square brackets are the log abundance of compared to now. And then the exponential terms are how it goes with half-life. So that's what enables you to go forward and backward. Exactly. So, and the 0.4, the 0.45, and the 0.15 are the proportions that heat the Earth today.
Yes.
So everything should be correctly scaled there. So that's energy in the numerator, and then amount of mantle you're trying to heat in the denominator, again, relative to the case to the Earth, which is, so as it says at the bottom of the paragraph, just underneath, the core is like 1/3 of the Earth's mass, and the mantle is 2/3. And the denominator of that equation I must have written wrong like 20 times to get it to scale correctly. But I think as published, it is now correct.
Yay! Yay!
Okay, so all you need to do is get your spreadsheet, in my case, and plug in the stellar abundances. So there are 4 abundances go in. And you almost don't need this stellar age. It's just kind of a check. So if the time you want to come out with, or the radiogen heat, the RH you want to come out, is when the star didn't exist, that's bad. So that's when the Gaia bit came in, and I had some help from them of how to interrogate the database and get these properties out.
Excellent.
So that's it. I mean, obviously I started this in lockdown, which was 3 years ago, but I make it look simple and elegant, I hope, at this point.
Let's take a look at the figure. Let's see what you got.
Yeah.
Okay, here we go.
Because I like plotting things in Excel, because you can make the points pink and
all kinds of colors.
You could probably do that in other packages, but for somebody who likes wrestling with data, this is a nice way to do it. So
very good. Time since first.
So in both cases, the y-axis is the time when continents could first appear, where 0 is the birth of the galaxy, and 12.5 billion years is the galaxy's age now.
Okay.
So you can see, if the calculation is correct, most of the continents for most of the sunlight stars, the 29 stars, are the gray points. They don't appear till fairly late in the history of the galaxy. And the reason for that is probably that stars born earlier in the history of the galaxy. So the x-axis is when the star was born. So some of them on the the left of the diagram are old stars that are now old. They probably had a lot of radioactive elements in the mantle, and so it was actually too radioactive for continents to form. Okay. So all this is scaled to the time at which continents appeared on the Earth, and remembering the radioactivity was falling while the mantle mass was presumably staying about the same. You need to get below a threshold for the continents to appear if these hypothetical planets are really Earth-like. And I haven't put in stuff like whether the amount of core made a difference to the physics of the mantle, because that's for somebody else to do. Right. But you get this result, you get this cloud of points, and then the diagram on the right is the same thing, but given we're not so certain of a lot of stellar ages, if you just plot it by abundance of iron on the x-axis, remembering that iron comes from supernovae, and so it builds up in the course of the history of the galaxy. So ones with lower iron that may be easier to get lots of numbers on tend also to be older stars. So the really interesting ones are the two pink ones, because I got a bit worried that all of these came basically from thorium studies that were really interested in solar analogs. Yes. And so I thought, well, let's try and find some that aren't solar analogs. And there's a couple of stars in the galaxy's thick disk, which is when the galaxy was really chaotic and just in its very early stages. So their birth time is like around 0 in the history of the galaxy. Okay. So those happen to have all the abundances, and those are the only two I could find. Right. And their continents appear so much lower down in both diagrams. They're low metallicity, low iron planets, but also very old, but they appear around when the galaxy was about 5 billion years old compared to us. Our continents appeared when the galaxy was about 9.5 billion years old. So we're talking about 4 or 5 billion years earlier. That's really interesting, I think. Cool.
Very cool. Very good. That's interesting. Very nice. And then we have some of the main features here. By about 2 gigayears. Okay. Cool.
Yeah, so that 0.5 is the one. Could there have been continents if these stars do have rocky planets? Yeah. Could they have had continents like a really seriously long time before us?
Interesting. Very cool.
Yeah, so the 6 points just came out of the diagram as diagnostics from this one equation, basically.
Very cool. Very nice. Okay. So we end up with a little discussion on more advanced models for RHT, right?
Yeah, so the big weakness in this is the assumption that you just have a threshold and your radioactive energy drops below some value that's too high. You go below the threshold and like your mantle solidifies a bit and your continents appear, which of course I'm sure is not the way it happens. And I think a week after I had this paper accepted, somebody came out with a new age for Earth's continents. So, you know, it's kind of deliberately shaky. It's meant to be like, what can you do? But you can easily, you know, remodel as we know more about the Earth. But I think the idea that the low metal systems are particularly interesting stands out really nicely. Yeah. So even if you redid the calculation and the numbers are off, if they could still be well ahead of ours, I think any rocky planets around these very old galactic stars would be super interesting.
That would be very
And I think there's been a bit of a bias against searching these for planets, because in the early days of planet searches, when you were mostly finding hot Jupiters, it didn't find them in the thick disk and the halo stars. And that's because they have low metallicity, and there was kind of never going to be enough mass to form a massive planet, or
fair enough.
for it to condense out of the disk. And so my guess is people stop looking a bit, but it might be an interesting time to go back and go, maybe there's no Jupiters and no Saturns, but there might be smaller rocky worlds. I have to say, I'm kind of guessing there, but I'd really like to know if Planet Searchers are really checking this out for some of the oldest stars.
Definitely. Very cool. Very nice.
And then I thought, well, let's look and see, have I just accidentally ruled out all nearby stars?
Oh, no.
And so, you know, everything we do with an expensive future observatory is not going to find any planets or continents. And I was really happy to find, for example, Habitable Worlds Observatory, which I think the launch date is suggested to be about 2040, by which time I realize I will be retired, but still very interested.
But you have a fantastic prediction here. So,
even by a quick look, there's plenty of overlap, because the ones that people look at for the metals in the stellar atmosphere tend also to be nearby stars.
Right.
So running the numbers as we have them at the moment, even just from this sample of not even 30 stars, there could be a couple with these old continents on. So I was really excited by that final result.
Very cool. It's pioneering. It's very lovely.
Yeah, thank you. It was meant to be pioneering and simple and easy to redo better.
Absolutely, but you know, first thing you want to do is just do the simplest things you can first when you're exploring, and so that's one reason that this one appealed to me. So
thank you.
It's very, very nice. Beautiful. Thank you, Jane, for walking us through your very lovely research note. And you've kind of touched on a little bit of, you know, things that people could do. And so on less than 40-year time scales, let's say 2 to 5 year time scales, you know, where do you think we go with this? Is it worthwhile doing additional searches for more nearby ones? Is there some advantage maybe to using different radioactive isotopes? Is there some theoretical work that could be done? Is there more observational work to be done? Just sort of next steps. Where do you think we go with this initial exploration over the next couple of years?
Well, there's definitely a lot of really nice theoretical work being done by people who really know what they're doing about what the surfaces of exoplanets, rocky exoplanets, would be like in terms of granite and basalt and, you know,
yes,
all these kinds of proper rocks made out of proper minerals.
I love it. Proper rocks.
Which I completely glossed over, not entirely understanding the word.
It was not heavy on the geochemistry.
Yeah, I really want to see, you need to know how the rocks make the continents. You need to know what the rocks are going to be and whether they like to make continents and that kind of thing. Right. The continents being important, as I didn't really say too much, but circulation of oceans and nutrients, and so having a lot of life on your planet rather than perhaps just, you know, amazing algae in the sea or something, but not you know, a huge biosphere. So the other thing is observations, because I've never tried to do this, but you know, it's obviously classic astronomy is taking a spectrum of a star and working out the abundances and pushing that to getting lower and lower abundances. But it tends to be done very, people are interested in a certain category of stars and the history of a certain element and a mystery about how that's made. So I would love to see this done more. So for example, there's no measurements of radioactive thorium in any M dwarfs, presumably because the lines are really hard to dig out.
Yeah.
But, you know, if you could do it, M dwarfs are a really interesting topic for people thinking about habitability. So a few measurements would be awesome.
Very cool. Very nice. Well, I really look forward to seeing this wild topic develop over the next couple of years. I think it'll be very lovely. Very cool. And Jane, thank you so much for walking us through your very lovely research note. Thanks.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.